Hey Precalculus friends, today we are going to be looking at section 7.1 day 2 notes, and we are going to be working on verifying identities, which is different than simplifying them. And I think in some ways verifying is easier because it's like a proof. You have to make one side look like the other, but the good news is you know what it's supposed to look like when you're done. So in some ways that's a little bit easier than not really knowing if this is the right answer or not. So what we're going to think about, or thoughts to keep in mind as we verify our identities, is that we want to transform one side of the problem into the other, okay? And this is important. Only work one side, okay? And we are going to typically start with the side that looks more complicated. A good rule of thumb. And I'll talk about that as we do our examples. You cannot move a term from one side of the equal sign to the other side. Okay, so don't try to move things back and forth like an equation. Your job is simply to make the left side look like the right side. Sometimes you may want or need to transform both sides, but this is very rarely going to be the case. Okay, it might happen once. And again, we're going to still be thinking about the ideas that we were using in our previous day's notes. Those 6 techniques that we were using, we're still going to be using those 6 techniques. So let's just get started with some examples. Our first example here, first of all, if you take a look at it, the left side looks a lot more complicated than the right side. Right? So our job is to show that 1 over secant squared plus 1 over cosecant squared equals 1. You're going to be delighted by how easy this one is. First of all, 1 over secant squared is a reciprocal identity. That's equal to cosine squared x plus 1 over cosecant squared x, another reciprocal identity, would be equal to sine squared x. And cosine squared x plus sine squared x, that is one of our Pythagorean identities. And so we know that these two things added together make 1. So there we have it. We're already done with the first example. We just showed that the left side equals the right side. In example number 2, again, left side looks more complicated than the right side, so we're going to start with the left side. And if we look at our numerator, 1 plus tangent squared theta, that looks like part of one of our Pythagorean identities. And if you look at your Pythagorean identities, sure enough, 1 plus tangent squared theta is equivalent to secant squared theta. So I'm going to rewrite that numerator as secant squared theta over cosecant squared theta. And of course, we want to make it look like tangent squared theta. Then the next thing is, it's much nicer to work in terms of sine and cosine if we can. So I'm going to rewrite our secant and our cosecant functions in terms of sine and cosine. I know secant is the reciprocal of cosine, so my numerator is going to become 1 over cosine squared theta. And my denominator, cosecant squared, that is the reciprocal of sine. So I'm going to rewrite that as 1 over sine squared theta. And then I'm going to keep switch flip because I've got a fraction divided by a fraction. So this is going to become, my numerator stays 1 over cosine squared theta times, but then I'm going to flip over that denominator, sine squared theta over 1. So now when I simplify this, I have sine squared theta over cosine squared theta, which hopefully you realize is tangent squared theta. Sine over cosine is tangent. So there we go. We have just verified example number 2. All right, let's take a look at example number 3. This one's a little bit different. In this one, my right side is actually more complicated than my left side. My left side is just sine x plus cosine x. So I'm actually going to work the right side. And in this one, my hint for you here is that we're going to split this into two fractions. I call this a love connection because if you take the bottom and you divide both pieces of the top by it, it sort of looks like a heart. That's a pretty sloppy looking one, but there's a heart there, sort of. So this is going to become two fractions. It's going to become 1 over secant x plus tangent x over secant x. That's going to be my first step. And then my next step is going to be to change everything to terms of sine and cosine. I know that 1 over secant, that's going to be cosine, right? Because secant is the reciprocal of cosine. So this is going to become cosine x. And then tangent and secant, I can both rewrite in terms of sine and cosine. Tangent is sine x over cosine x. And secant is 1 over cosine x. So because those cosines are both on the bottom, they're going to cancel out when I keep switch flip that. So I just end up with cosine x plus sine x, which is the same thing as sine x plus cosine x by the commutative property. So there is example number 3 verified. Example number 4. We are definitely going to want to work the left side on this one. Okay, this looks a lot more complicated on the left than it does on the right. And the first thing that I'm going to do is I am going to distribute on the left side, and I'm going to see where that gets me. So when I distribute that sine theta to both terms, my first term is going to become sine theta times, cosecant theta minus, and then sine theta times sine theta is sine squared theta. All right, now the next thing is cosecant theta is the reciprocal of sine. So this expression is really sine theta times 1 over sine theta minus sine squared theta. So sine theta on the top, sine theta on the bottom cancels out. So then I just have 1 minus sine squared theta. Now hopefully you're thinking, ooh, that looks like a Pythagorean identity. If sine squared theta plus cosine squared theta equals 1, and I subtract that sine squared theta over to the other side, then 1 minus sine squared theta is equal to cosine squared theta, which was what I was trying to get to. So example number 4, verified. Example number 5, I'm going to work the right side on this one. It looks a lot more complicated, and I think the first thing that I'm going to do is I'm going to start by trying to find a common denominator for these two expressions. Okay, and obviously I've got two different denominators here, so I know my rules, right? I've got to put both original denominators into my common denominator. I'm also going to chop slash that negative and give it to that 1. So my first step here, my common denominator is going to be 1 minus sine x times 1 plus sine x. And then the first numerator is going to get multiplied, the number 1 is going to get multiplied by 1 plus sine x, and then that negative 1 is going to get multiplied by 1 minus sine x. So my new numerator, 1 times 1 plus sine x, is just 1 plus sine x. Plus, now remember I am distributing a negative 1 through my second binomial here. So negative 1 times 1 is negative 1, and negative 1 times negative sine x is another positive sine x. So if you look at my numerator now, there's some simplifying that I can do, right? The 1 and the negative 1 are going to cancel out, and then I have sine x plus sine x, which is going to make my numerator 2 sine x. And then in my denominator, if I FOIL that out, that's a sum and difference pattern. And when you FOIL a sum and difference pattern, it always makes a difference of squares. So my denominator, after FOILing, is going to become 1 minus sine squared x. All right, we just had this in our previous problem. 1 minus sine squared x, that's a Pythagorean identity. So I can replace 1 minus sine squared x with cosine squared x. So now I've got 2 sine x over cosine squared x. We are almost there. So all we're going to do is we are going to think about cosine squared as being written twice. So our numerator is still 2 sine x, and then our denominator, cosine squared, is cosine x times cosine x. So this is where we kind of have to think creatively on this one. So if we look at what we're trying to make, we're trying to make 2 tangent x times secant x. Well, tangent is sine over cosine. So 2 tangent x would be this part right here. And then if I put a 1 right here, 1 over cosine x, that's my secant x. So there we go. Example number 5, verified. Finally, we have example number 6. And in example number 6, I am going to work the left-hand side. And I'm going to start by saying this one is probably the most challenging of all of the examples so far. So before I dive in here, I really want to think about what I have and what I'm trying to get to, okay? When I look at this, what I notice is, and I'm going to pause here for a second and jot something down. So I just paused to jot this note down here, and that is that when I look at this problem, and specifically when I look at the right-hand side, I've got secant and tangent, right? So secant and tangent both have cosine in their denominator, because secant, remember, is 1 over cosine, and tangent is sine over cosine. So I need to introduce something on my left-hand side that could somehow get us a cosine going in our denominator. Right now, all I have is 1 minus sine u in the denominator. So this is a situation where I am going to multiply by a conjugate, top and bottom of my expression. Let me show you what that's going to look like. So in my numerator, I have cos u. In my denominator, I have 1 minus sine u. So if I multiply top and bottom by the conjugate to 1 minus sine u, that's going to be 1 plus sine u. And what that is going to do for me here, first of all, in my numerator, I'm going to do distributive property. In my denominator, I am going to FOIL. But when you FOIL conjugates, you end up with a difference of squares, right? So in my numerator, when I distribute the cosine u, I'm going to end up with cosine u times 1 is cosine u plus cosine u times sine u is just going to be cos u sine u. But then my denominator, 1 minus sine u times 1 plus sine u, we just saw this in a previous problem, that's going to give us 1 minus sine squared u. And then the next thing that I'm going to do is I'm going to replace that 1 minus sine squared u, which again we've seen multiple times today. I'm going to replace that with a Pythagorean identity, which 1 minus sine squared u would be equal to cosine squared u. So now on my numerator, I'm going to have cos u plus cos u sine u. And in my denominator, I'm going to have cos squared u, okay? And that's, again, my Pythagorean identity. And now I'm going to use my pretty love connection again here, right? And I'm going to say that I can divide, trying to make this look more like a heart here. There we go. So I can divide both of these things by cosine squared u. So I get cos u over cos squared u plus cos u